So this is the second part of our momentum notes. We're going to talk about conservation of collisions. This part needs to come after you've already watched Momentum and Impulse intro video. So in the intro video, you learned, hopefully, that momentum is a measure of the inertia of moving objects. And there's a law that says that in the absence of external forces, the momentum of a system or the object remains unchanged. We call that the law of conservation of momentum. In science, conservation just means that the total doesn't change. Okay, so the easiest way to just think about this is that in a system, objects have inertia. They don't want to change, right? And so in the absence of an external force, they're not going to change. Other laws that might be familiar to you would be probably from chemistry. So in chemistry, you probably learned about the conservation of mass in your reactions and formulas. You also probably learned about conservation of energy. So there are a lot of areas in science where we think about conservation meaning total amount not changing. So we generally apply this law to scenarios where you've got more than one object and those objects are going to crash into each other. And we would say that a system is including the two objects that are going to crash. And we can say that the net momentum or total momentum of the whole system, so object 1 and object 2, before the collision, will equal the net momentum of both objects after the collision. And that even is true if the objects change direction, change speed, change what they were doing. Total momentum is still going to be conserved. We actually have 3 types of collisions that we're going to take a look at. There are more types. We're simplifying a little bit. We're also going to just do this conceptually. So if you're following along on the notes, there are example problems that I'm not going to work out here. You don't have to do them. We're trimming this down a little bit for the sake of time. So just concepts here. Okay, so we're going to talk about elastic collisions, we're going to look at inelastic collisions, and then we're going to talk about explosions. So, perfectly elastic collisions. This is basically the most perfect possible scenario you can have where momentum is conserved, always, unless there's an outside force. In a perfectly elastic collision, your two objects are separate from each other before the collision, and then they collide, and then they bounce off and they separate from each other after the collision as well. So in the equation, we see that in this way, we would say that the momentum of object 1 initial is separate from the momentum of object 2 initial, but if we add them together, we get a total, right, before, and then the momentum of object 1 after the collision continues to be separate from the momentum of object 2 after the collision, but we can total those together and see that the totals are the same or conserved. So the example from real life that I can give you for this would be when you're playing pool and you shoot a billiard ball towards another one, like in this first picture. You might have a ball sitting at rest here and another one moving with some kind of positive velocity. They're going to collide, and then that second one is going to zoom forward, right? It wasn't moving, now it is, so we can say it's sped up, and then the first ball is going to continue moving, but it's going to be slower. Okay, but again, there's space between them, they don't travel together. Another example of how this might play out is you might have an object or a couple objects like the ones on the bottom here, where one is going in one direction and one is going in the opposite direction, and then they collide and then they bounce off. But because they've switched directions, again, we can still say momentum in total is conserved. The second type of collision is called a perfectly inelastic collision. So this occurs when your two objects start out separately. Okay, so in this one we've got a positive initial velocity and then we have an object at rest. Your objects collide, and then they travel together, so there's only one final velocity. So the equation looks a little bit different. We can say that the initial momentum of object 1 and the initial momentum of object 2 are separate, but then because they travel together, there's only one final velocity. We don't have to say P1 or P2. Again, this total has to be equal to this total because momentum is conserved unless there is an outside force. A third type of interaction is technically not a collision, but an explosion. So if you look at this picture up at the top here, your typical explosion, you've got all the pieces here together, right? This is before the explosion. And then you've got the explosion, and after, you've got all these little pieces that are flying away with different final momenta, potentially, but they're all in different directions. And so because of that, the initial and the final totals are still going to be able to be equal. Okay, so that's not just with what you would think of it with an explosion. You could also think of it with, say, two people that are maybe on skateboards or roller skates facing each other. They're going to push each other apart and move away from each other. Or in the picture here, down here, you've got two carts together that have an initial momentum. Generally, that initial momentum is 0. Usually the object's not moving before the explosion. Okay, then after the explosion, you've got one cart moving in one direction, and you've got the other cart moving in the opposite direction. So you've got two separate final momenta, but those two separate final momenta are in opposite directions, and so your total initial is still going to equal total final. Okay, so those are our three types. Let's try a little conceptual / mathematic example here. So in this example, we've got Granny and her grandson Ambrose. They're roller skating. Ambrose has decided to sit still for some reason. So he has an initial velocity of 0, while Granny is whizzing by. So she's got a fast velocity. We're going to say Granny is object 1, and Ambrose is going to be our object 2. Okay, and then we're going to look at this table here first. So they want us to find Granny's initial momentum before the collision. So momentum is mass times velocity, so we would do 80 kilograms times 3 meters per second. And when we do that, we see that Granny's initial momentum is 240 kilogram meters per second. Okay, then we can do the same thing for Ambrose. His initial momentum is going to be 40 kilograms times 0 meters per second, and so we see that his initial momentum is 0. So we're going to call that P2I. And then we want to know the total momentum, so total is going to be P1I plus P2I. And when we add 240 plus 0, we get a total of 240 kilogram meters per second. Okay, so this number here is our total initial momentum. Okay, if you notice, after they collide, Granny picks up Ambrose. She doesn't want to knock him over, so she just picks him up and skates with him. So think about what type of collision this is. Is it elastic? Is it inelastic? Or is it an explosion? The right answer here is inelastic. In inelastic equations, we see, or collisions, we see that the two objects start separately, but after they collide, they travel together. And so you have one final momentum. Okay, so if we head over now to these conceptual questions over here, Letter B says, after the collision, does Granny's speed increase or decrease? Well, she's picked up Ambrose, so the total mass is increased, so she's going to slow down. Letter C, after the collision, does Ambrose's speed increase or decrease? Well, he wasn't moving, now he is, so he's definitely increased. Letter D, after the collision, what is the total mass of Granny and Ambrose? So Granny had a mass of 80 kilograms. Ambrose had a mass of 40 kilograms. And so we have a total combined mass of 120 kilograms. Letter E, after the collision, what's the total momentum of Granny and Ambrose? Well, what does the law of conservation of momentum say? It says that PI, initial total momentum, is equal to PF, or final total momentum. So if we look at our initial, then we would say that the PF has to be the same. It has to be 240 kilogram meters per second. Okay, so that brings us to our last question here. We want to know, how fast are Granny and Ambrose moving after the collision? So we're going to use our equation. We're going to simplify a little bit and say that initial momentum is equal to final momentum. If we write that out, we can say initial momentum is equal to mass 1 plus mass 2 times VF. The initial momentum was 240 kilogram meters per second. The combined masses was 120 kilograms. We did that in letter D. We're looking for final velocity. So to solve, we're going to divide both sides by 120 kilograms, and that gives us our final velocity for both Granny and Ambrose of 2 meters per second.